Okay. All right. We'll be starting here shortly. We got 2 minutes to go. Okay. 10:30. Everybody's got to get in here. I'll resend the invite just in case people are confused. There they come. There they come. Okay. Good to have you all in here. Need a few more to get in here before we start. Mm-hmm. All right. There comes a few more. Welcome. Hi, Willie.
What's going on, man?
Good to see you. All right, we're up to 7. Come on, y'all. Let's get in here.
They probably still in the David. He was still talking in our microbiology class. I just left out of
Oh,
there.
okay.
He was
Okay.
still, and he was still
Gotcha.
giving a lecture. I don't
Yes,
think
you guys had a class that ran over.
yeah, I don't
Okay.
think he realizes we have classes back to back.
Gotcha. Gotcha. Here they come. Okay. Okay. All right. Okay. All right. We got pretty many in here now. So today we're going to start a discussion on what's in your diet. Okay. Now, your diet, in terms of energy, is made up of 3 main components, right? Fats, carbs, and proteins. But they all have different roles, right? Fats and carbs we eat primarily for energy, for life, and protein we eat for building blocks, right? We eat protein to make protein. So essentially, when you're eating meat, what your body does is it mechanically and chemically breaks it down into its amino acids, and then your body takes those building blocks and rearranges them to build the proteins that make up you. Okay. So, in terms of energy content per molecule, the fats are the champ. Okay. More calories in fat than there are in carbs, more calorie in carbs than there are in protein, and protein brings up the rear. And this is why one of the ways you can effectively diet is to go for a diet that's high in protein and high in fiber, right? Because the protein has minimal energy content and the fiber has none. And that is a diet that will make you feel full, but won't have a huge calorie payload, right? So it's one of the ways you can cut down on your calorie intake. Now, in order to talk to you about fats and carbs and later on proteins, we have to talk a little bit about chemistry so that we don't get the cart before the horse. Okay, so bear with me here. And what we're going to discuss is kind of the universe around you, right? Way, way back in the beginning of time, this is billions of years ago. Okay, everything in the universe was concentrated into a single point, which physicists call a singularity. And that represented an unstable state that led to a gigantic explosion, which you probably know as the Big Bang. And when the Big Bang happened, the universe was created. And there's only 3 things in the universe: matter, energy, and empty space. Okay. Matter is anything that has mass and occupies space. And the 3 states of matter are solid, liquid, and gas. And you can convert between those states by changing things like pressure and temperature. Okay. Energy is the ability to do work, and it comes in many different forms. There's potential energy, which is the energy that is contained as a result of position or state. And then there is kinetic energy, which is the energy of movement. And you can convert one energy type to another. And then the third thing is empty space. And empty space is just empty space. There's nothing there. Okay. So energy is the ability to do work, and you can transform energy from one type to another. An example is here with this guy shooting an arrow.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
So what you're seeing is energy transformations from chemical energy in the muscle tissue to kinetic energy in the muscle tissue. That's how the muscle is able to shorten. That energy gets transferred to the bowstring in the form of tension. So that's a type of potential energy. And then when he lets go, the potential energy in the bowstring becomes kinetic energy transferred to the arrow. The arrow zips across to the target, and that energy gets released as pressure, heat, and sound. Okay. Now these changes always give off a little bit of heat, and what that heat does is it sort of disorganizes the universe. So when the universe was created, two laws went into effect, and they're called the first and second laws of thermodynamics, and they're pretty easy. The first law of thermodynamics states that energy and matter can't be created or destroyed. So there's no magic, right? I can't wave a wand and make something appear out of nowhere or make something disappear. Okay.
Mr. Converse,
Yes.
I'm sorry. The password is nutrition
Nut
100, right?
100. Yeah, Nut 100 should be all caps, I think.
That's what I'm saying. You said it's not the 100?
Nut, N-U-T.
Oh, okay.
Nut 100.
Capitalized.
Capitalized.
Yeah.
Yeah.
Okay. It was just two people that was trying to get in. That's all.
Gotcha. And the second law of thermodynamics states that if we're looking at a system like water in a glass or air in a room, that system is going to organize itself in the low energy state. Okay. And that's essentially what you experience around you. For instance, when you like, if you put on perfume before you go out, okay, that perfume will spread from your body to the air in the room, right? And that's a low energy state. That's taking the molecules of the perfume and distributing them evenly in the air that surrounds you. And you didn't have to do anything for that to happen. It just happened automatically, okay? It's like water rolling downhill, okay? Water on a peak will roll downhill because that represents a low energy state, right? It'll seek its fluid level, its bottom, all right? And you don't have to do anything for that to occur. You can resist those changes in a system. For instance, we could keep water from rolling downhill by using pressure, okay? But then we're putting energy into the system, and that results in a change, all right? So those are the two big rules that govern everything around us, right? Can't create or destroy energy or matter, and everything tries to take the easy way out, okay? So different types of energy, chemical energy, and the connections between atoms, which are the building blocks of matter, electrical energy, which is the movement of charged particles. Particles have an electrical charge, either positive or negative. Mechanical energy, which is force applied to matter to move it. And then electromagnetic energy, which is an unusual kind of energy that can move through a vacuum, okay? And includes things like X-rays and radio waves and visible light, okay? And it's called electromagnetic because it has an electrical and a magnetic part to it. In fact, kind of interesting, if you've ever seen pictures of or been to Las Vegas, one of the things that you notice, besides people losing money, is lots of lights, right? And you ever wonder where all that electricity for Vegas comes from? If you go north of town, you'll see a big dam called the Hoover Dam. And it created Lake Mead when they dammed up the Colorado River. And what happened was Lake Mead filled up behind the dam, and that represented potential energy in the water because of the elevation of the water level, right? The water at the top of the lake has more potential energy than the water at the bottom. So what they do with that water is they let it flow over the dam. And when it flows over the dam, inside the dam, they have turbines, big wheels with a copper coil in the center. And the wheels have, like for spokes, magnets. And what happens when the water spins the turbine is that the magnets spin around the copper coil, and that creates an electrical field in the copper coil. And that's the juice that powers all of Las Vegas. And that's called hydroelectric power. And that represents energy transformation, right? Potential energy from the water becomes kinetic energy for the water as it falls, which becomes kinetic energy to spin the turbine, which becomes electromagnetic energy because it moves a magnetic field around a copper coil, and that creates an electrical field, and that's current, and that powers all the lights in Las Vegas. Same thing you can see if you go to the junkyard and see cars dropped in the crusher, right? If you want to pick up a big heavy car, you use a magnet on the end of a chain, okay? And that's an electromagnet. What happens is that big iron disc doesn't become a magnet until we run current around it. And that creates a magnetic field in the iron disc. We pick up the car, and then when we want to drop it in the crusher, we cut the current, and the car falls in the crusher, and we smash it, okay? And so that's another example of electromagnetic energy, right? A moving magnetic field makes an electrical current. A moving electrical field makes a magnetic field, okay? And those are all energy transformations, and they all result in the production of heat, and all that heat makes the universe more random, okay? And that's what makes the universe more disorganized, and that's what causes systems in the universe to try and find the low energy state, okay? So when we convert energy from one form to another, we lose a little bit as heat, and that makes the universe less organized, okay? Matter is made up of elements, which are simply components, substances that can't be broken down into anything simpler using chemical techniques. And every element has unique physical and chemical properties, right? The physical properties we can see and detect, like, does it conduct heat or electricity? Can we bend it? Okay. Is it hard or soft? All right. Chemical properties are, how does it play with the other elements, right? When we get them together with other elements, what do they do? Do they hook up? Do they come apart? What happens? Okay. Atoms are the tiniest pieces of an element that still maintain all the properties of an element. Okay. And the atom is a very old concept. It comes from the ancient Greeks. A guy named Democritus didn't have anything to do one day. He was staring at a boulder, and he reasoned that If he took that boulder and split it in two, you'd have two smaller boulders, but they'd still have the properties of the original. If he did that again, he'd have four even smaller boulders, but they'd still have the properties of the original. And he reasoned that he'd eventually get to a point where he couldn't do that anymore. And he would call that particle the atom, which is the smallest piece of something that still has the physical and chemical properties of the biggest piece. Okay. And that's the working definition of the atom that we have today. All right. The atomic symbol is a 1 or 2 letter chemical shorthand for the element. Okay. And this is an example of a helium atom. All right. Helium is the gas that they filled a Goodyear blimp with as it flies over football games, is lighter than air. That's why it floats. Okay. And you can see that there's a couple of different models for the atom. All right. We've got the orbital and we've got the planetary model. So if we're looking at the orbital model, all right, what you see here is a cloud where particles called electrons that have a negative electrical charge can be found in a sphere at a specified distance from a region in the middle of the atom called the nucleus. All right. And then in the planetary model, the electrons orbit it like the Earth orbits the sun. Okay. The nucleus of the atom, which is in the center, contains particles called protons, which have a positive electrical charge, and neutrons, which don't have an electrical charge. And most of the mass of the atom is in the nucleus. And then outside the nucleus are electrons, which move at the fastest speed anything can move, which is the speed of light. Okay. And they stay where they're put, right? They stay in their planetary path in this model or in their sphere in this model, right? Okay. And a lot of times, the first time you hear this, maybe in high school, you write all this down and you nod your head and say, okay, that's the way it is. All right. But if you think about this model, it kind of doesn't make any sense, right? Because if you look at it, the middle of the atom is positive and the stuff outside it is negative. And so in your world, our world, the thing should collapse or explode, right? Because similar charges repel each other and unlike charges are going to attract. So why doesn't that happen? And the answer, and you're going to love this, that comes to us from many, many decades of research is that we don't know. Okay. This is an example in science of what's called a model. All right. And what a model is just a representation of what we know right now. And models are incomplete because the more we learn, the more we add to the model and the model will change. Okay. So what we do with models is we take what the model gives us and then we work with it. Okay. So there's a whole bunch of things we don't understand about the atom, like why did the electrons stay there and not go in between, right? Why does the nucleus hold together and not fly apart? We don't understand that. Okay. Something is working, but we don't know what that something is yet. Okay. When we identify elements, what we do is we count the number of protons in the nucleus in order to identify which element it is, right? Hydrogen has 1 proton in the nucleus, helium has 2, lithium has 3, right? And that's called the atomic number. The atomic number is just the number of protons in the nucleus, and it identifies the element absolutely, okay? In a normal atom, the number of protons and the number of electrons are the same, okay? And that means that the atom is electrically neutral. For instance, helium has 2 positive charges in the nucleus and 2 negatives outside. Hydrogen has 1 positive in the nucleus and 1 negative outside, and so on, okay? And it also turns out that in the atom, there are rules for how many electrons can be in each shell, which is the path that the electron orbits around the nucleus, right? The first shell can hold 2, the second shell up can hold 8, and the next shell up can hold either 8 or 17, depending on how many we load in there, okay? So why is that? Why is that the way things are, all right? Well, the reason, and we're going to see in a minute, is because that represents a low energy state for the atom, all right? So that's the atomic number, right? The number of protons in the nucleus, we can write that as a subscript to the left of the symbol, like that's lithium, and that's your 3 for atomic number. The mass number is basically the number of protons and neutrons in the nucleus, okay? The neutrons have mass, but they don't have any charge. So if we look at the Facebook of the elements, it's called the periodic table, all right? Now, this is kind of amazing because if you think about the universe as infinitely large, this is all the matter in the universe right here, fits on one piece of paper, right? Which is pretty amazing, but there it is, all right? And what you'll see is columns and you'll see rows, right? These are columns, right? And these are rows, right? So what do we have in each box? We have the symbol for the element. And then above it, we have the atomic number. And then below it, we have the atomic mass, okay? So hydrogen, atomic number 1, atomic mass 1. Over here, helium, atomic number 2, and atomic mass around 4, right? You'll notice that in the atomic mass numbers, you don't get a nice round number. Sometimes you have digits after the decimal point. And the reason for that is that when the universe was created, each element has some atoms in it that were a little heavy, meaning they had some extra neutrons in the nucleus. So the atomic mass is just an average weight, right? So if you went out, for instance, and you collected a basket of carbon atoms, right? And you divided the weight of the basket over the number of atoms in the basket, you would get 12.01 grams per mole of carbon atoms. And a mole is just a count. Like a dozen is 12, a mole is 6.02 times 10 to the 23rd of whatever we're talking about, okay? So it's a really honking big number, all right? That's just the way it is for every element, right? There's going to be some atoms in there that are a bit heavy. The reason that we care about that in healthcare is because these heavy versions of elements sometimes give off energy that we can trace, and they're called radioactive isotopes. And we can use that to ask questions about the body, right? For instance, radiation that comes from radioactive elements like uranium can be used to generate X-rays that we can see bones in your under your skin, and we can look and see whether or not there's a broken bone there. Okay, we can inject you with contrast dye, which has radioactive molecules in it, and we can ask questions about your blood vessels and see if they're broken, they're leaking, or if they're blocked. Okay, we can give you radioactive glucose, and we can ask questions about how your brain is working without having to open up your skull and actually look at your brain, right? So that's why we talk about radioactive isotopes in courses like anatomy and physiology and here in nutrition, okay? Now you'll notice something else. There's different colors here on this periodic table. You'll see this little stair step here that I'm tracing with the red dot, right? And that's the dividing line between the metals and the non-metals, right? The non-metals are on the right, and the metals are way over here on the left, okay? And then there's a special column at the end, and these are called the noble elements, all right? And what's unique about them is they don't do any chemistry. They just hang out. They're found in their pure states in nature. So by definition, that means they're already in their low energy state. So if they're in their low energy state, all the rest of chemistry, which is the making and breaking of chemical bonds, is nothing more than trying to have an arrangement of atomic particles like these noble elements have, which basically means that they're trying to fill their outer shells, okay, by either gaining, losing, or sharing electrons, because electrons are what are involved in chemical bonds, okay? So metals, what's unique about them? Well, they tend to conduct heat and electricity. They're easy to bend. They're frequently very shiny, okay? In chemical reactions with non-metals, these guys over here, they tend to give up electrons and take on a positive charge. And in nonmetals, we have material that's a poor electrical and thermal conductor, all right? And in chemical reactions with metals, they tend to gain electrons and take on a negative charge. So they form things like salts, okay? And we'll see an example of that in a little bit. When nonmetals react with each other, they tend to share electrons, which means that they'll have a pair of electrons that spend some time with atom number 1 and some time with atom number 2. And that is like a rope that holds them together. And covalent bonds are very powerful, very strong, okay? And sometimes that sharing is equal between the two elements, and sometimes it's unequal. If the sharing is unequal, we call that a polar covalent bond, and if it's equal, we call it a nonpolar covalent bond, okay? And then, if you're curious, when metals react with each other, they form things called alloys, and they have something called metallic bonding, which is beyond the scope of this course, okay? So essentially, what's driving all of chemistry is to try and be like these guys in the orange column over here, right? They want to fill their shells and be low energy and be happy, be stable, okay? The columns are arranged so that the light stuff is on the top and the heavy stuff is on the bottom. The rows are arranged so that the light stuff is on the left and the heavy stuff is on the right. So the heaviest stuff in the table is down here in the lower right, and the lightest stuff is up here in the upper left, okay? Chemical bonds are just connections between atoms that hold them together, okay? And there's two kinds of chemical bonds that latch atoms together within a molecule, and they are ionic and covalent bonds, okay? In an ionic bond, an electron is given up by a metal and picked up by a nonmetal. They take on opposite charges, and the opposite charges hug each other, okay? And they form things like salts, like sodium chloride or calcium chloride. In a covalent bond, what happens is that the two elements get together and they share electrons between the atoms, and that's what holds them together, all right? It's the electrons in the outer shell of each element that do the work of chemical bonding because they have the most energy, because they have the most potential energy. They got the most juice in them, all right? And so they're the ones that are going to do the work, all right? The valence shell is the same as the outer shell, all right? And what controls most of the chemistry that we're interested in is something called the duet rule for hydrogen, right? And the octet rule for the rest of the elements that we're interested in. And the duet rule just says that hydrogen wants to have 2 electrons in its outer shell, and the octet rule says that for the elements we're worried about, they want to have 8 electrons in their outer shell, okay? So you can see here with the elements that are in that last column that their shells are full up, right? There's helium, 2 in the first shell, that's max occupancy. You can't stuff any more in there. Helium is found in its pure state, okay? So when you get a pocket of helium, it's helium gas, that's all there is, okay? Neon, another element in that last column, has how many in its outer shell? 2, 4, 6, 8 electrons, right? So it doesn't do any chemistry. It hangs out in its pure state. But these other guys, the outer shells aren't full up, right? Hydrogen's got 1, he can pick up 1. Carbon's got 4, he can pick up 4. Oxygen's got 6, he can pick up 2. Sodium has 1, but what sodium will do, instead of trying to pick up 7, he'll do the easier thing, right? And he'll kick this guy over to a nonmetal, and then this shell underneath has 8, and that's a full shell, okay? He'll take on a charge when he does that, but that's okay. That still represents a low energy state for him, right? Sodium is a metal, right? Carbon and oxygen and hydrogen are nonmetals. So those are the 3 kinds of bonds. Ionic bonds and covalent bonds are within a molecule. Hydrogen bonds are something different, and they're between molecules. And we'll talk about those probably a lot later on, okay? In an ionic bond, a metal and a nonmetal get together, and the metal will punt the electrons in its outer shell, and the nonmetal is going to pick them up. So what will happen is that the metal will take on a positive charge and the nonmetal will take on a negative charge, and that'll pull them together, and they'll stick to each other. Okay. The negatively charged element is going to become an anion. That'll be the nonmetal. And the positively charged one is going to become a cation, and that's the metal. Okay. And that results in an ionic bond. So you can see an example here, right? Sodium and chlorine, right? So if we were at school, right, and I were to bring sodium into the school, I would have to do it under kerosene, okay? Because sodium is so reactive with water that when it hits water, it explodes. It bursts into flames in an effort to form something called sodium hydroxide, right? And if you've ever been around chlorine, you know when they're chlorinating a pool that it's very corrosive, right? It'll burn your skin, burn your eyes, bleach your clothes, right? But when you get sodium and chlorine together, what happens? This electron in the outer shell of the metal is going to get kicked over to the nonmetal, right? Chlorine has 7 in its outer shell. He can complete his outer shell with 8, right? And what happens now is they take on opposite charges and they hug each other. And that's sodium chloride, and that's table salt. That's what you put on your French fries. So how is it that you can take something that's explosive and corrosive and turn it into something that you eat? And the answer is we've changed where the electrons are. And as a result, we've changed the chemical properties, because now this is a molecule, whereas before over here, these were elements, pure elements. Okay. When you look at a salt crystal, you see something very interesting, right? You see that the sodium ions and the chloride ions are arranged in a way that makes them hug each other effectively, right? The positive charges are surrounded by negatives, right? And the negatives are surrounded by positives. Why is that? And the answer is that's the easiest way to set them up. If they're going to hug each other, let's get them switched off, right? So that the negatives and the positives can attract and the whole thing holds together. And that's the second law of thermodynamics, which says that in a system, we try and set things up so that the system doesn't have to use a lot of energy to stay that way. And that's exactly what we see with the salt crystal, all right? If I were to try and force things and make all the sodiums go to one side of the cube and all the chlorides go to the other side, I could probably do that, but that would take a lot of energy to happen, all right? And so second law of thermodynamics says easy way out, let's do it like this, okay? Now, one of the things that'll happen with something like salt, you know that if you take a tablespoon of salt, you throw it in water, it'll dissolve, right? That means it'll go clear and you'll have salt water. The reason for that is that the water molecules have polar covalent bonds in them. And we'll get to those in a minute, but that means that the water molecule itself has a slightly negative and a slightly positive end. So what happens in water is the water molecules kind of stick themselves in between the sodiums and the chlorides, and the ions come apart and they float around in the water free, okay? And that's called dissolving, okay? You always know that you have a solution because the solution will be clear, all right? So things that are salts, that are basically ionic compounds, or things that are polar covalent compounds will dissolve very easily in water. And that's just a rule that says like dissolves like, right? And that's just another example of the second law of thermodynamics, okay? Now with covalent bonding, we have a little bit of a different situation. In covalent bonding, what we get is two nonmetals getting together, and they try and set things up so that they can fill their shells, but everybody is going to be stable, right? So we can take 4 hydrogen atoms and 1 carbon atom. Carbon's got 4 in the outer shell, so he can pick up 4. Hydrogen's got 1, so he can pick up 1. So look what happens. They buddy up, and we get full shells for everybody, right? So if we count, right, 2, 4, 6, 8 for carbon, that's a happy carbon atom because his shell is full and he's low energy. And let's look at hydrogen. 2 for this hydrogen, 2 for this hydrogen, 2 for this one, and 2 for this one. Those are happy hydrogen atoms because their shells are full too, right? You get to count the shared electrons for both the hydrogen and the carbon atom, okay? That's a stable compound. That's methane, okay? And that's going to not change over time unless it encounters some other molecule that would like to make things even more stable by reacting with the methane. Okay. But that essentially is a covalent bond, right? When carbon and hydrogen share electrons, that bond is an equal share, so that there's no negative or positive zone created in the molecule. And when identical nonmetals hook up, that's an equal share. And those are called nonpolar covalent bonds. Some examples are here, right? Nitrogen has 5 in the outer shell, so he can pick up 3. So he buddies up with another nitrogen atom and he makes a triple covalent bond. And if you count, right, the math works out. 2, 4, 6, 7, and 8 for that nitrogen. 2, 4, 6, 7, and 8 for that one. And that's a triple bond, and that holds those two molecules together real easy. Okay. It's very strong. It's 3 times stronger than a single covalent bond. Oxygen's got 6. He can pick up 2, right? So when 2 oxygens get together, what do? They make a double covalent bond. 2, 4, 6, 7, 8 for that one. 2, 4, 6, 7, 8 for this one, right? So 2, 4, 6, 7, 8. Equal sharing, nonpolar covalent bond, all right? In a polar covalent bond, you got different nonmetals attaching to each other. And so the sharing's not equal. The sharing is a little bit more with one than the other, all right? So it's kind of like a timeshare, right? If you get a timeshare down in Florida, the more money you throw in, the more time you get to spend on the timeshare, and then the other people end up having less time at the timeshare, okay? So it's the same thing here with this polar covalent bond, right? One atom spends more time with the electrons than the others, and the result is that the attachment between them has a negative and a positive end to it. That's a polar covalent bond, all right? Atoms that have a greater ability to pull electrons towards them are called electronegative atoms, and atoms with a reduced ability to do that are called electropositive atoms. So the electropositive atom in a polar covalent bond will have a slight positive charge. The electronegative atom will have a slight negative charge. And water is an example of this, okay? In water, the hydrogen is the electropositive and the oxygen is the electronegative. So the electrons spend more time with the oxygen. This would be like a diagram showing you the relative amount of time the electron spends with each element. And the result is that the water has a positive and a negative end to it, all right? Now, why do we make such a big deal about this? Because polar things and charged things like to get together. They like to dissolve in each other, okay? Because that represents a low energy situation. Because things that are charged can flip and flop their negative and positive ends and buddy up, okay? Whereas things that aren't charged or polar like to get together with themselves, okay? So this is just another example of like dissolves like, okay? An example of something that's non-polar would be like oil or grease, okay? You know that you can't dissolve oil in water. In fact, if you pick up a bottle of Italian salad dressing and you take it off the shelf, you notice that the oil is floating on the top and the water is underneath, okay? The reason for that is that the oil is nonpolar and likes to associate with itself, and everything underneath is either polar or charged and likes to associate with itself. If you add energy to the system by shaking the salad dressing bottle, you form a temporary mixture called an emulsion. By adding energy, what you've done is you've created a situation that's a high energy state. But if you set that bottle down and wait, what's going to happen is that the oil and water will separate. The oil will get with the oil, and the water and everything that's charged or polar will get with itself, and you'll have separation again. And that's the low energy state, okay? That's the second law of thermodynamics at work, helping us to understand how the universe around us operates, right? So what you're looking at here is an example of these connections between atoms and how the sharing works, right? In an ionic bond, there is no sharing of electrons. The electrons spend all their time with the non-metal, okay? In a polar covalent bond, the electrons spend more time with the electronegative atom than with the electropositive one. And in a non-polar covalent bond, the sharing is totally equal, all right? So the bottom line is non-polar, or if you like, greasy stuff, likes to get with greasy stuff, right? Whereas polar or charged stuff likes to get with polar or charged stuff. And that's just second law of thermodynamics at work again, okay? If you get grease on your hands, right, and you put it under just water, it's not going to come off, right? How do you get it to come off? Well, you use soap, right? Well, what's special about soap is that soap has a polar end and a non-polar end, okay? The non-polar end of the soap lifts up the grease. The polar end of the soap attaches to the water, and you make these little soap bubbles with the grease inside, and the grease goes down the drain, okay? So that, again, is just good old second law of thermodynamics, okay? We will come back in 15 minutes at 11:30, and we will finish out the rest of this, okay? So let me adjust the time here so that it says 11:30. And then I will also take attendance at that point, because by then everybody should be in here. So let me make that 11:30, all right? And I will see everybody in 15 minutes.
Okay.
Is anybody else lost?
Lost as hell.
'Cause I don't know what the
If
fuck
you're
going on.
lost,
I don't even know what he
If
even
you're
talking
lost,
about.
if you're lost, listen to me. If you're lost, that's,
You were supposed to be on
that's
break.
what Friday at
Right.
5 to 7 is for. That's what Friday at 5 to 7 is for. Remember, this whole thing is taped, so you can watch it again. All right. But if you have a question about what we talked about, that's when you come back and you find me and you ask me where you got lost. Okay.
I thought you was on break. We was on break.
We are. I just heard somebody saying they were lost.
Oh, okay.
Now you been.
I'm still lost. Shit. Man.
Jenny,
Hey.
we gonna do that. Y'all want to do it today or do y'all want to wait?
Today.
Say today. That's the best
Yeah.
time for me.
Me too, 'cause I'm about to.
So do we got to be there at 2:15 or is it 1 to 3?
It's 2:15, how it was before.
I'm gonna come up there earlier though, cause I'm about to leave UC. I'm about to just come up there.
Yeah, I'm
Gonna be able to.
Willie, how you feel being the only guy in the class?
Yeah, I'm good. I'm the only guy at work.
You at work?
I said I'm the only guy at work, so when I'm in class, hi.
This shit confusing as hell. I don't even smoke.
And I don't know what.
I don't know where to start, what to look. I'm like, and then he just said this.
Ronnie, you was supposed. I called you this morning.
Who?
She know who I'm talking to. Ronnie.
Oh.
She probably got him.
I was asleep when. And I called you last night. You ain't
I
answer
know, cause I was asleep too.
Yeah.
Hold on.
Anybody else got live at 4:30?
Y'all better go, cause she gonna make y'all. If y'all got lab, y'all better go, cause she gonna make y'all redo it over, and she gonna count it against y'all.
Who got
I was
lab?
gonna say that.
She gonna count it against you. She gonna make you. Yep. This the second one. If you missed the first
two.
Yep. So
Said
go.
that when she busted in our class the other day.
Even if you late.
Who all got lab at 1 o'clock? Because there was some people missing from our class.
I got mad at 2.
Yeah, it was only us, me, Gina, Mariah.
Last time. But I figured it was supposed to be a lot more people in there though.
Yeah, she said.
She said about 7 to 8 per group.
Julia.
Yeah.
Julia, you coming? Is your lab today?
Yes, today, but I think she said 4:30. I'm about to call her and see.
Yeah, I will double check. If you don't go, they are definitely gonna try to hold that against you. which I think is
Wait.
bogus. And I think
Wait,
that's
is
super
this
being
215 or 1? I'm so confused right now.
ours is 2:15.
It
Okay,
say
yeah.
one on our schedule. On our schedule,
It
say
says
1 to
1 o'clock.
3.
That's
Everybody
the
says
old
1.
schedule. That's the old
Right.
schedule, but our new one 215, right?
Right.
I got a little time.
I better double check because mine is a couple of separate classes. So it's a class
No.
from 1 to 2:15, 2:30 to 3 something, and another one
Oh
at
no,
4.
I was just doing this.
Who was that? Genesis.
Yeah.
Then you say yours was one yours right before our lab at 1.
Yep.
Okay.
The lab at 4:30 is actually 4:45.
Chrissy.
Yeah.
I'm about to go.
Let me mute.
My son gonna have goddamn roaches in this room.
Let me go get some chips out of the closet.
Oh, that's right over there.
You want to hear me though, Brittany? Let me go get some chips and pop out of the refrigerator. My stomach's so I know. In the lobby, the living room. She's in the living room. Hey, I better shut up before he come looking for me.
Man, I feel like we just started this and I'm just lost in this house. Man, I just recently placed $1,300.
Anybody else having difficulties with this?
Say what?
With what?
Whole class, I don't even know what he's talking about. What the hell does molecules and atoms got to do with
Ooh,
nutrition?
me either. I don't know. I'm lost. I've been lost 3 classes ago.
We had 3 classes.
No, that's how lost I am.
Oh, girl, I'm like, oh.
No.
I had to call the school this morning to make sure I was in the right class. I'm like, why is he talking about atoms and molecules? Ain't that chemistry? This said nutrition. I guess. I didn't misplace my money. Hell, I do that. Misplace $1,300. What purse did I have? Come on.
I need to get that.
Did he already start doing attendance, calling the names?
I'm not going to call names till I get everybody off the visible roster here. So
Oh, okay.
let me get everybody that I can see here. Good one. Yeah.
Hey, Zena, you ready for this run through today?
Yes, ma'am, I am.
Don't pass me, Terry Roper.
Okay, gotcha.
Did you figure it out yet? Yeah. Burger King. All right.
Hey, Mr. Converse, if we have questions about the homework and stuff that's due next week, can we email you?
Sure. Okay. All
Sorry,
right.
but you missed my name.
Okay, hold on. Let me go through, and for the people I didn't see, Raven Bennett.
I'm right here. Hello.
Here we go. Erica, let's see. No. Rashia Frazier. Do we have Frazier? Okay. Zenib.
Yep, here.
Okay.
I wonder if she knows her class today. Let me text her and ask, do she know? I'm gonna text Rashia.
Darian McGee. No. Sheila Taman. Okay. So
Yeah, Raven, make sure you text her because it's the second class she missed.
Yeah, Frazier.
I need Frazier.
I
don't think she know that her class is. She might have got it confused. Sorry.
Frazier, McGee, and Tamang.
I'm texting Rashia now.
Okay. go. We need McGee.
Yeah, she here.
You here? Zarian?
No, Rashia. Oh no, yeah.
I'm looking.
Is that Shalina or something? Hold on.
Tamang.
Yeah, that ain't Rashia. That ain't.
I meant that's who I meant.
Oh, okay.
I need Rashid.
I wonder.
And I need Zarian. So I need Frazier and McGee.
Oh, I thought that. No, I just text her. I don't.
All right. Well, I will take a. Print this.
I gotta get my daughter. This gonna pick me up.
And let's check it. All right. So it's those two. All right. Okay. All right. All right. We're back. Now we're going to talk a little bit about organic compounds, which are compounds that contain carbon and hydrogen. Okay. The reason these are important is because this is what you're made out of mostly. Okay. Are compounds that contain carbon. You're made out of protein. You're made out of carbohydrate. You're made out of lipids. Okay. So you literally are what you eat. Carbon is used as the basis of life because carbon can do one thing that the other elements in the periodic table can't do, which is that carbon can form rings and chains with itself, which means you can build a lot of very interesting stuff using carbon, okay, including the tools of life, which are proteins. So this is why life is based on carbon. When you look at a living thing, most of the molecules that it's made out of are going to contain carbon, right? Now, most organic compounds are polymers, meaning that they are repeating chemical units hooked to each other like a chain. Okay, an example of a polymer would be a protein. Protein is a chain of amino acids. A complex carbohydrate is a chain of simple sugars. Okay, a nucleic acid is a chain of nucleotides. And so when we build a chain, that requires energy. And so we usually take the energy from another molecule, and that molecule is something called ATP. And when we tear up a chain, energy comes out, all right? The reactions that make up life are called metabolism, right? And metabolism can be broken down into reactions that build things and reactions that tear things up. The reactions that tear things up are going to be reactions that give off energy. And the reactions that build things are going to be reactions that use energy. So this is why we have to eat in order to live, right? The energy in the food that we eat is used to do the work of building and maintaining our body. Carbohydrates are a type of energy source, okay? They have a chemical formula, CH2O, where in the molecule, the number of carbons and oxygens is the same, and there's double the number of hydrogens in the molecule, okay? Examples of carbohydrates would be things like table sugar, okay, or molasses, okay? Carbohydrates in your diet are primarily for energy, all right? The average minimum amount of carb needed for the brain is 130 grams a day. Median carb intake is about double that among men 20 years and older, 256 grams a day among women in the same range. So why more for men than women? Well, men are bigger, okay? The acceptable macronutrient distribution is 45 to 65% of your calories, meaning that 45% of what you eat in a day should be carbohydrate, all right? So what are some examples of dietary carbohydrates? Well, there's things like starch, all right? Now, where do you get starch? Primarily from your plant material like potatoes and rice, okay? Other sources of sugar include certain vegetables like sugar beets, okay, and sugar cane, which is where we get a lot of our table sugar from. Fruits provide lots of sugar. And of course, you can get sugar in things like candy, right, where you basically extract it from the fruit or the vegetable, and then you use that to make something else that you eat, all right? The reason that you want to limit the amount of carbohydrate to 45 to 65% is because if you go over that, then you're likely to be taking in more calories than you're going to burn. And that means you're going to gain weight, and that's going to make you unhealthy. Okay. So the nervous system has to have carbohydrate in order to function. Okay. As well as the heart. All right. And then all the other tissues in our body can switch off between carbohydrate and protein or lipid. Okay, so the body is set up so that when we're in a pinch, we always try to save the carbohydrates in our diet for our brain, our brainstem, our spinal cord, and our peripheral nerves. And then those other tissues that can switch off will switch off to create the energy that they need to do work. Carbs are classed according to the number of simple sugars that make up the molecule. Okay, so a monosaccharide is a single ring sugar. A disaccharide is a double ring sugar, and a polysaccharide is 3 or more. Okay, examples of disaccharides include sucrose, lactose, and maltose. Lactose is milk sugar, sucrose is table sugar. Okay, polysaccharides include starch and fiber and glycogen. Okay, well, we already know where starch comes from. That's the plant's version of stored energy. That's its fuel. And we get that from, again, things like potatoes and rice and so on. Fiber is a different sort of molecule. Fiber is a polysaccharide that we are unable to digest. And so it passes through our system without going into our bloodstream, which means that it comes out the other end. So there's no calorie content in fiber for us, okay? Now the bacteria that live in our colon can use the fiber for energy because they have the tools to do that. We don't, okay? So this is why, again, if you eat a high protein, high fiber diet, you can cut the number of calories that you take in while at the same time feeling full, okay? Monosaccharides, glucose, that's blood sugar. Fructose, that's fruit sugar, okay? And galactose, there's other monosaccharides as well, all right? They all taste sweet, okay? With the exception of the polysaccharides, starch, fiber, and glycogen. Now, glycogen is what we call animal starch, and we find that in white meat, okay? Like the white meat in chicken or the white meat in pork, okay? And in your body, you have white meat, okay? White meat is basically muscle that can work real fast but gets tired real easy, okay? So those are different types of carbs. When we generate a polymer, right, we use energy. An example here is a dehydration synthesis reaction where we take two monomers that have an OH group attached to them. We remove the equivalent of a water molecule and we hook them together. So it's like hooking links in the chain. And to do that, we need energy, and that usually comes from ATP, all right? When we do the reverse, we take the chain and we bust off pieces of it, and that's called a hydrolysis reaction. Hydro means water and lysis means to split. So we use a water molecule, we crack this connection, and now we take off a link in the chain and we use it for something else. You can see an example here with the monosaccharides glucose and fructose being connected to each other with this top arrow here to form sucrose, right? And if we go in the other direction, we use a water molecule to split this connection and we generate glucose and fructose by themselves, okay? Now, this is a drawing of a sugar molecule. Some of the carbon atoms are shown, right? But others are implied. Each bend in the ring here represents carbon atom, okay? So there's a carbon here, 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 and here, right? So how many carbon atoms total? 1, 2, 3, 4, 5, 6, okay? Same thing over here. How many carbon atoms? 1, 2, 3, 4, 5, 6, okay? So that's just the idea, is it's a way to sort of draw a molecule easy without showing every single atom, okay? So these reactions where we build a chain from tiny pieces, those are called anabolic reactions, and they take energy in. And these reactions where we take something big and tear it up, those are called catabolic reactions. And we split off pieces of the chain to use for more energy. Carbohydrates include sugars and starches. Most of them are polymers, and they have the same number of carbons and oxygens in the molecule, and they have double the number of hydrogens, okay? So as an example, glucose has 6 carbons in it. So the overall formula for glucose would be C6H12O6, okay? Where the numbers down here indicate the number of atoms in the molecule. And then the different classes, right? Monosaccharide, single ring sugar, disaccharide, double ring sugar, polysaccharide, 3 or more, okay? And what are they for? They're for energy, but they're also important in building things like DNA and RNA, which are information molecules in the body, all right? They're used to serve as instructions for building the tools of life, which are proteins, okay? Carbohydrates are also used on the surface of cells to indicate whether or not that cell belongs in the body and whether your immune system should leave it alone or attack it and kill it, okay? You can see some examples of sources of carbohydrate, right? Monosaccharides like glucose and fructose and galactose, okay? And the different sources, right? Corn syrup, fruits, and milk. And this is energy, right? Disaccharides like table sugar, milk sugar, again, energy, all right? And then polysaccharides, for such as starches and fiber, okay? We get this primarily from our vegetables and our fruits, all right? Their function is energy storage as a starch molecule in the plant, right? For us, it's an energy molecule, right? When we eat starch, we break it down, we tear it up, and we get the energy out of it, right? The fiber passes through our body without providing us any energy because we don't have the tools to break it down, okay? There's an example of a monosaccharide, right? The same formula up here as we talked about earlier, right? Let's look at glucose, right? How many carbons? 1, 2, 3, 4, 5. There's 6 carbons. How many oxygens? 1, 2, 3, 4, 5, 6. How many hydrogens, right? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then there's a 12th one, okay? Okay, over here. So that's the same formula, right? C6H12O6. Same for fructose, right? Now it looks different than glucose, but the reason is that the way that the atoms are hooked to each other is in a different order, all right? And so those are called isomers of each other. Glucose and fructose and galactose are isomers of each other. They all have the same chemical formula, right? But the way they're hooked together is in a different order. And then some examples of sugars with 5 carbons, right? This is deoxyribose. How many carbons? 1, 2, 3, 4, 5. And this is ribose. How many carbons? 1, 2, 3, 4, 5. Okay. This is a part of a building block for DNA. This is part of a building block for RNA in the body. And we also get this in our food, and in our vegetables, our fruits, right? Because every living thing has information molecules in it. When we eat it, we break them down, and we use them for energy. Disaccharides are double sugars, and they're too large to pass through the lining of the digestive system and into our bloodstream. So we have to break them down into their monosaccharides in order to get them across the lining of the digestive system and into the blood. And then from there, we carry them to the liver, which will store them for a time. And then later on, the liver will release them into the blood when our blood sugar levels fall between meals. Okay, so some examples of disaccharides are sucrose, maltose, and lactose. So let's take a look at disaccharides.
Sometimes organisms link sugar molecules in pairs to form disaccharides. Here are several examples. Plants make sucrose by joining glucose and fructose. Sucrose circulates in plant sap, and we obtain it from sugarcane and sugar beets and use it as table sugar. Lactose is formed by joining galactose and glucose. Lactose is the disaccharide that gives milk its sweet taste. Maltose consists of 2 linked glucose molecules. Digestion of starch in a sprouting seed or in the intestine of an animal produces this disaccharide.
So when we eat these, we break them down, right? There are tools called enzymes in our digestive system that break these connections, and then we take in the monosaccharides into the blood, and from there it goes to the liver, okay? Polysaccharides are just longer chains, 3 or more single sugar chains attached to each other. Fiber, starch, and glycogen are some examples. Because they're so large, they don't dissolve as easily in water as disaccharides or monosaccharides do. So let's take a look at polysaccharides.
Polysaccharides are polymers, long chains consisting of hundreds to thousands of linked monosaccharides.
So you can see here that these are all chains of glucose, but the attachments are a little bit different, right? The attachment in cellulose is different than the attachment in starch. The attachment in glycogen is a little bit different, okay? There are branches in glycogen that aren't in starch. We can break down starch and glycogen because we have the tools to break these hookups, but we don't have the tools to break these hookups. So it's kind of like having a key for a particular lock, right? We have the key to unlock these bonds, okay, but we don't have the key to unlock these. So they stay attached to each other all the way into our colon. Cellulose is found in fruits and vegetables. It's an important component in regularity and in colon health, right? It helps to cut down on the rates of colon cancer. It keeps you regular because it can attract water to it from the tissues around the colon, and that makes the fecal material looser and easier to pass. As we get older, our colon gets slower, and the more time the fecal material spends in the colon, the more water gets pulled out of it, and the harder the fecal material becomes and the harder it is to pass. So if we have fiber in our diet, that doesn't happen as easily, and we're able to pass the fecal material more effectively. That's why as we get older, we increase the fiber in our diet, and we may even take fiber supplements. The liver is going to convert fructose and galactose into glucose, which is blood sugar, and this lifts your blood sugar levels, and that causes insulin to be produced from the pancreas. The insulin is the signal for the body tissues to pull the glucose out of the blood and into the cells and use it for energy. The body digests 95% of starch between 1 and 4 hours after ingestion. Digestion occurs mainly in the small intestine using pancreatic amylase to reduce complex carbohydrates into disaccharides. Glycogen is the stored carbohydrate that's found in liver and muscle tissue, and it's an important backup energy source in the body, but we only have a tiny amount of it. Most of our energy is stored in the body as fat, okay? In order to maintain expected glucose levels between meals, glucose is released through the breakdown of liver glycogen, okay? So when you eat the white meat in a bucket of chicken, all right, the reason it tastes sweeter than the dark meat is because of the glycogen in the meat, okay? And that's also the reason that it has a higher carbohydrate content, okay? We have muscle tissue in our body. Some of it stores more glycogen than others, and that reflects the kind of job it does in the body. The muscle tissue that has a lot of glycogen in it is what we call fast twitch muscle, which means it does heavy jobs very effectively, but it's easily worn out, okay? Whereas the muscle tissue that we have that has less glycogen in it is more for endurance work, like the muscles involved in things like walking and jogging, okay? Digestible carbohydrates are going to give you 4 calories per gram, and that puts them at second place in the energy sweepstakes. Fiber is a carbohydrate, and it's found in plant foods, but we can't digest it. This includes things like pectin, cellulose, oligosaccharides, and gum. It's important for bowel movement because it adds bulk to the feces by drawing water into the feces. And that also helps muscle contractions called peristalsis that help us to eliminate it when we have a movement. There's also important studies that show that fiber can lower cholesterol and reduce the incidence of intestinal cancer, although we don't quite know how that works. Total fiber is 25 grams a day for women and 38 grams a day for men. Those are minimums. You can go more than that if you want to. Now, lipids are a different type of fuel molecule, okay? Examples of lipids include triglycerides, which are made of a molecule called glycerol connected to 3 fatty acids, and phospholipids, which are made from triglycerides by stripping off a fatty acid and adding a phosphate group to it. And then sterols, which are a hydroxyl group connected to a fused ring system from something called cholesterol, okay? Triglycerides are built from fatty acids, and these include saturated and unsaturated fatty acids. Saturated fatty acids have more calories in them because they have more carbon-hydrogen bonds, and unsaturated fatty acids have fewer calories in them because they have fewer carbon-hydrogen bonds, okay? If you want to determine the number of relative calories in an organic molecule, all you have to do is count the number of carbon-hydrogen bonds. The more carbon-hydrogen bonds there are, the more calories there are in that molecule, okay? So you can see here an example of a lipid called a triglyceride, all right? These are insoluble in water. And why is that? Because they don't have polar regions in them, all right? They don't have covalent bonds in them where the electrons are unequally shared, which means they don't have a negative and a positive zone anywhere in the molecule, okay? Which makes them greasy or oily and makes them more likely to dissolve in other things that are greasy or oily, okay? So when you think organic and nonpolar, think high calorie, think greasy, okay? This is a look at how a triglyceride is built.
Butter, lard, margarine, and salad oil are composed of lipids called fats. To make a fat molecule, 3 fatty acids bind to a molecule of glycerol. For this reason, Fat molecules are technically called triglycerides. Fat molecules do not mix with water because they have 3 long hydrocarbon tails. Cells use fats for energy storage because the tails hold more potential energy than other biological molecules.
So this is one of the reasons why, if you eat a lot of fat, you're going to gain weight, right? What your body does with the extra calories that you don't burn is it stores it as body fat. And there's way more calories in a molecule of fat than there is in a molecule of carbohydrate. Now, you can still gain weight on carbohydrates by eating more of them, right? But fat is the calorie champ. Triglycerides are called fats when they're solids and oils when they're liquids, okay? Triglycerides tend to be liquids when they have unsaturated fatty acids in them, and they tend to be solids when they have saturated fatty acids in them, okay? So oils have unsaturated fatty acids and have fewer calories than fats like Crisco or lard or butter, okay? Main functions are energy storage, insulation, and protection, okay? And again, you can see down here how we build them, right? We build them by attaching these fatty acids to this glycerol molecule with a dehydration synthesis, so that uses energy to happen. And then in this form, the energy is stored in the body as body fat until we use it later, okay? So this is like the main molecule in the body's pantry is triglyceride. Body fat is important because it provides insulation, it pads and protects internal organs, and it holds in body heat, okay? And it's also a major source of fuel because since the molecules are nonpolar, and that's another way of saying they're hydrophobic, they don't like to get with water, right? You can store a lot of calories in a tiny volume, okay? If we tried to store the same number of calories in carbohydrate as we store in fat, the body would be enormous because you'd have to have water in order to dissolve all of those polysaccharides, okay? So this is the go-to molecule for the body's pantry, right? The triglyceride. And our body has the ability to convert parts of this molecule into blood sugar so that it can be used by the central nervous system, by the rest of the tissues in the body, and then the other tissues in the body can use either sugar or it can use the fats, the fatty acids that are attached to the glycerol. Saturated fatty acids have single covalent bonds between the carbon atoms, and so they have a lot of carbon-hydrogen connections, which means they have a lot of calories. And those include lard and butter, okay? Unsaturated fatty acids have one or more double bonds between carbon atoms. That reduces the number of carbon-hydrogen bonds in the molecule, and it reduces the number of calories in the molecule. And those include plant oils, such as olive oil or peanut oil. And that's why they're called heart healthy, because they're less likely to promote a condition called atherosclerosis, in which fatty plaque deposits on the arteries and makes the artery space where the blood goes narrower, and that causes your blood pressure to go up, and that makes it more likely you're going to have a stroke or a heart attack, okay? Trans fats are the type of saturated fat that's used in snack foods, all right? Like combos and Fritos and Doritos, all that stuff that we love to eat, but it's unhealthy for us because it has a lot of calories, but it doesn't provide much of a sense of feeling full, okay? So the reason that trans fats are used in snack foods is because they don't decompose as quickly. They don't go rancid, all right? If we didn't use trans fats in snack foods, then you'd have to be swapping out the snack foods every day, right? And that wouldn't be a very profitable way to provide people snacks. So the use of trans fats is not a plot to make us all unhealthy. It's simply a consideration of how long the product can stay on the shelf. So the main thing to understand with trans fats is you want to reduce the amount that you consume, okay? So cut trans fats down in your diet as much as you can. Omega-3 fatty acids are heart healthy fatty acids, and we can get those from things like avocados and fish, okay? Phospholipids are a type of lipid that takes a triglyceride and then it removes one of the fatty acids and attaches a phosphate group to it. The reason that phospholipids are important is because they are the building blocks of cell membranes. The cell membrane is the outer boundary of the cell that allows the cell to control what goes in and out, okay? It allows the parts of the cell to stay in one general area, and it protects the cell, and it also serves as a way for the cell to detect what's going on around it, right? The cell can put proteins in the phospholipid layer that is its cell membrane, and those proteins can tell the cell what's going on outside so that the cell can respond to it. You can see here that a phospholipid has different regions, all right? The phosphate group here has a charge on it. There's frequently a group that contains a nitrogen attached to that. It's called an amino group, okay? It has a positive charge. So this end of the molecule is charged. This part of the molecule is polar, and this part of the molecule is nonpolar, okay? So this is the greasy part, and this is the water-soluble part, okay? So we say that this is the polar head, and these are the nonpolar tails. And so when you throw this in water, what it'll do is it'll either form a bubble with the polar heads facing the water and the tails facing each other, or if we're very careful about adding the phospholipid, it'll form a bilayer where the tails are in the core of the bilayer and the heads are sticking out on either side of it, okay? Sort of like a lipid sandwich. And that's essentially what a cell membrane is made out of, okay, is a phospholipid bilayer. That's important because that means only nonpolar components can cross the membrane without help, and the other stuff that the cell needs, if it's polar or charged, has to come through a gate, and that gate is usually made of protein, and the cell can determine how many of those gates it has and how many of those gates are open or closed. So it allows it to determine what goes in and what goes out, okay? Sterols come from a molecule called cholesterol. We get that mostly from our meat and our dairy. It's not an essential nutrient because the liver can make cholesterol from other stuff. But if we take in too much cholesterol, it builds up in our tissues and it contributes to atherosclerosis, right? The deposit of those plaques on the artery walls that raises our blood pressure and puts us at risk for heart attack and stroke. You can see what they look like here, okay? It's a lipid because, again, it's mostly carbon and hydrogen, just like a triglyceride is. And again, each bend in the ring represents a carbon, okay? So there's lots of carbon, hydrogen in here. Examples include vitamin D, steroid hormones like estrogen and testosterone and aldosterone and cortisol, and bile salts, okay? Bile salts are essentially molecules that are used like a soap in order to emulsify the fat in our diet. When the fat in our diet from our stomach goes into our small intestine, the bile salts from our gallbladder mix with that, and then they break up those big lipid droplets into tinier ones, and that makes it easier for the enzymes that break down the fat to do their work, okay? Cholesterol is important in our body because it's the starting point for making steroid hormones and vitamin D, and it's also critical in controlling the movement of phospholipids in the cell membrane. So it kind of acts sort of like a doorstop does on a door, right? It can control how much the phospholipids in the cell membrane move around. By sticking more cholesterol in there, they move around less, okay? Eicosanoids are made from fatty acids. They include prostaglandins, which are important in blood clotting and inflammation and labor contractions. And then other lipids in the body include the fat-soluble vitamins A, D, E, and K, and lipoproteins, which are combinations of cholesterol and protein and triglyceride that act like a vehicle, like a car, to carry around lipid-soluble stuff in the blood. Because again, something that's oily or greasy isn't going to mix very well with blood plasma, which is mostly water. So it needs a carrier, and that's what the lipoproteins are for. They get inside the carrier, and then the carrier takes them to their destination and drops them off. So the chemical group known as lipids come from things like dark meat, poultry skin, dairy, and things like margarine, butter, shortening, oil, and lard. Fat is essential for the body. It serves as a concentrated form of energy, okay? And it's also how we insulate the body, hold in our body heat, pad and protect our internal organs. And it's also how we store the maximum number of calories in the minimal space, okay? It's critical for hormone production, providing material for cell membranes, and padding for vital organs, and insulation for body temperature. And it's also important for nerve function. It's part of a molecule called myelin, which is used to insulate nerve cell endings so that our electrical signals in the body go where they're intended, okay, and go there quickly, all right? Kind of like the insulation around a wire in your home. It also is important in the absorption of fat-soluble vitamins, because something that's fat-soluble is going to dissolve in something else that's fat-soluble, all right? And that's how it's going to get carried around the body or stored in the body. Triglycerides are 98% of the fat in our food. They combine with glycerol to supply energy to the body. They let fat-soluble vitamins get transported and stored in the body, and they make adipose tissue that protects our internal organs and also insulates our body and provides an energy storehouse. Saturated fatty acids are solids at room temperature. Think lard, butter, Crisco, and are found from animal sources. Unsaturated fatty acids, think oils, okay, come from plant sources and reduce health risk because they have fewer calories in them. Sources of unsaturated fats include olive oil, canola oil, avocados, peanuts, okay. Polyunsaturated fats have even fewer calories in them, and they include corn, wheat germ, soybean, safflower, sunflower, and fish oil. Essential fatty acids are made from broken down fats that have to be eaten in order for us to have them in the body. Essential fatty acids include omega-3 and omega-6 and help with blood clotting, blood pressure, inflammation, and other parts of metabolism, okay? So in your diet, you have to remember that you have certain things that your body can't manufacture, right? The essential fatty acids and the essential amino acids are examples of that. You have to eat them in order for our body to have them. The others our body can make from other things. The recommendation for fats is 20 to 35% of our total calories. 10% or less should come from saturated fat, and cholesterol limited to 200 to 300 milligrams a day. A diet high in fat is linked to cardiovascular disease, hypertension, and diabetes, okay? Why? Well, again, with a high fat content in the diet, you're more likely to deposit fatty plaque on the walls of your arteries, and that's going to cause an increase in blood pressure. That's hypertension, and that makes it more likely that you're going to pop capillary beds in your brain and have a stroke, or pop them in your heart and have a heart attack, or pop them in the retina of your eye and go blind, okay? It also causes blood to clot more easily because in areas where the plaque is, the blood flow slows down. And when blood flow slows down, blood tends to clot. Okay. And those clots can jam in capillary beds and make a stroke or a heart attack as well. Okay. The diabetes comes from the fact that if you have a diet that's high in carbohydrate or calories and doesn't make you feel very full, then you make a lot of insulin. And over time, you can become less sensitive to the insulin. And the result is that you end up with a condition called type 2 diabetes, where the sugar that comes from your diet ends up staying in your blood, and that causes your blood pressure to go up. That causes nerve endings to die. That leads to early onset blindness, and it's generally associated with obesity and hypertension. Okay. The exception for this is children under 2 who need a higher amount of fat in order to make brain tissue, and that primarily is the myelin in the brain tissue. A diet with less than 10% fat can't supply enough essential fatty acids and results in a condition called cachexia, where the person looks like skin and bones. Most lipid metabolism happens after fat reaches the small intestine. That's where the gallbladder will squeeze the bile into the duodenum, which is the first part of the small intestine, and that causes the mechanical breakdown of fat droplets into tinier droplets, and then lipase from the pancreas will finish the process off. And once that happens, we can take those breakdown products and put them into the lymphatic system, and eventually that fatty lymph, which is called chyle, will work its way back into the blood, and from there it'll be carried to the liver, and then from the liver to the rest of the body. AMDR for fats, again, is lower than carbohydrates because of the calorie considerations, okay? Intestinal cells absorb most of the end products of digestion. Some of it ends up in the feces. Very low density lipoproteins are going to carry triglyceride to the cells. Low density lipoproteins are going to carry cholesterol to tissue cells, while high density lipoproteins remove cholesterol from the cells and take it to the liver, okay? So if you've ever had blood work done, one of the things they do is your cholesterol and your triglyceride levels, and they have what they call good and bad cholesterol, right? The good cholesterol are the HDLs. That means your body is in a cholesterol scrubbing state if the HDL levels are high, and that means you're less likely to have plaque in your arteries. Whereas the LDLs and the VLDLs and the chylomicrons, that's the bad cholesterol, and that means that your body is more likely to deposit plaque on your arteries and make you more at risk for cardiovascular disease. Lipids are the calorie champ. They provide 9 calories per gram of energy, and as a result, they are the densest form of stored energy, okay? So this is one of the reasons why the body stores our energy as lipid, but it's also the reason why you want to reduce the amount of lipid in your diet so that you don't take in more calories than you burn and gain weight as a result, okay? So again, the watchword is to make sure that you have high fiber, high protein, and that puts you at less of a risk for cardiovascular disease, all right? So let's do one more quick check here. I need to see who was I missing? I was missing Rashia Frazier. Did she ever?
And me, Mr. Converse.
Okay, and Zaria McGee. Is that Zaria?
Yes, I'm here. Yes, I was supposed to come back at 11.
Okay, but is Rashia Frazier here?
She here.
She's here. Okay.
She here. It's on. It's saying she here. She here.
She's here. Okay. All right. Now y'all got your notes. And you got your homework last night. I sent it to you, but it's also posted on the website. Okay, so if you didn't get it in the email, you can always get it on the website. You can download it, and the calorie or the fat and the carbohydrate homework, I believe, are due next Thursday, if I'm not mistaken. Let's check the syllabus real quick. Yeah, fats. You also go fats and carbs. So both of those are due Thursday, 10/29. So that's next week. So you want to get that to me before next week. Okay. The information to answer the questions in those homeworks are in the notes. But if you have other questions, just email me and I can get back to you. Okay. And then next week, we're going to talk about protein, which are the tools of life. And we're going to talk about cardiovascular disease. Okay. And you'll get your second homework, which is about proteins. And then you'll get a practice exam 1 to get you ready for the actual first exam in the class. Okay. All right. So does anybody have any questions before we bump out?
Oh, as long as you got my name on that attendance, I'm cool.
Yep, I got everybody now. Everybody came. So we good.
Mr. Converse,
Yes.
is this our first homework assignment?
It's the first one that's due quick. I gave the disease project out last week, but that's not due till week 8.
Yeah, but say I know I'm tripping.
Okay, and how soon is the lecture going to be available? Because I'm totally lost in what's going on.
Okay, the lecture is going to start to load right after we cut class, and it should be up by 2 o'clock, and I'll send you guys a link.
So by 2 o'clock?
Yeah.
Well, is there a book?
Yeah. Okay.
It's online.
There is a book. Let me show you. Okay. So I will send this to you, but on Google Bookshelf, I've got 2 books that are useful. Let's see here. That's Vital Shore. Google Bookshelf.
Because no book was provided through the school, right? No.
Well, there was, but it's not. It's just a pamphlet. Okay. And it's not a great book. And I sent it to you. So let me pull this up. So on Google Bookshelf, I'll send you these links. I've got a couple of books. Let's see here. My subscriptions. I've got a couple of books on nutrition that sort of talk about what we're doing instead of just giving you a bunch of charts. And I think it's useful. Okay. What I will do is I will send you the links to those books. Let's see here, books.
I got a book for
Yeah.
nutrition.
Yeah, I've got a couple of books that I think are really good.
Well, I got 2 actually.
Yeah, but like I said, I'll send the links to you, and you can use them as reference. Okay, because like I said, the book that they provide with the course is really sparse. Okay, and this book I think will help you understand what we're talking about a lot better. Yeah, I'm not seeing the link right off the top of my head here, but I'll send it to you guys along with the link to the lecture. And I think that'll clear up a lot of confusion and help you guys understand the material better. Okay, so just wait for that. That'll be coming from me this afternoon. Okay. Any other questions before we go?
No.
Okay, I'm going to stay out the class because I probably got some additional questions and everybody else probably don't. That's okay with you, Mr. Converse.
So, all right, so I'm going to bump out.
Before you bump out, I mean, can you hang tight because I have some questions that, I mean, everybody else may not have have questions.
Okay, all right. Well, I'll hang with you.
I got a quick question.
Yes, sir.
That Adobe app, do we submit our homework on it or?
Yeah. So let me show you where that. So there's a link that I sent you guys to get it. Okay. So
Using, man.
show
I
you how to
download
get it.
it. I don't know how to-
Download Adobe Acrobat Reader. Okay. So you go here and you're going to go to the link that I sent you. Okay. And
Can
then
we do it both ways, Mr. Richard? Can we email it to you or send it to you that way? Can it be either or?
Yes, you're going to have to send me your completed homework for me to get it because, like I said, there's nowhere to post it. You just have to email it to me. But anyway, you just hit download Adobe Acrobat Reader, okay, and it'll take you to a website that'll give you the reader for the version of the computer system you're using, and that's what you use to open up and complete the homework. It has to be Adobe Acrobat Reader, or else you won't be able to type in the form fields that are in the homework. Okay, so if you have trouble getting that, like when you open the homework up, let me show you what it looks like. So you go here, and I'll open up. Let's open up like this is the carbs. This is the carbs and fats form. This is your notes, right? See these blue areas? You can type in here, right? And then you can, whatever you want to say, right? And for your homework, right, you open it up and let's go to the carbs homework, for instance, okay? You can type an answer in here, right? And then don't worry, it'll just keep it. And that way everything kind of stays where I expect it to be, and it's easier for me to grade, okay? And you don't have to worry about having to have like Microsoft Office or something to work on it because Adobe Acrobat Reader is free. So you just download and install that and it works. If you try to open it in your web browser or some other application, the form fields may not show up and you won't be able to complete it, okay? So just use that link that I sent you and you'll be in good shape, okay? It'll download right to your machine and you'll install it and you'll be ready to go, okay? Any other questions? Are we good?
No, they was gonna leave and I had some more questions.
Okay, what's your question? Go ahead and ask.
So this class seemed pretty challenging. What's the success rate on this? Cause
most people pass with flying colors.
What you say?
Most people pass with no problem. They get the grade they need. Again, the main thing is just to complete the homework and get it submitted because, like I said, I give you guys the information you need in order to get through the exam and score well, right? That's what the practice exam is all about. The chemistry chapter is challenging because most of you've never had chemistry or never had anatomy and physiology, right? So this is the first time you're seeing this, okay? And that's why we try to take it slow, all right? And if you have questions, this is the time to ask, okay? But we have to talk about chemistry in order to talk about proteins and carbohydrates and fats, right? Because if you don't know what an atom is or what a molecule is or what a chemical bond is, you're not going to know what a fat or a protein or a carbohydrate is. So that's why we have to introduce this stuff in order to help you understand, right? So we take it a little bit at a time, okay? And then as you have questions, as you work on the homework and look at the text, it'll sink in a little bit easier, okay? And like I said, once I get you the link to the textbook that I've put on Google Bookshelf, I think that'll help a great deal because the textbook that comes with the class is basically a review book. It assumes that you've already had a nutrition course. So what we need is a book that sort of introduces the concepts. Any other questions?
So another question.
Yeah.
Normally, do you take this class before you take anatomy, or is it vice versa?
Well, it depends on your program. It depends on your program. A lot of people are taking this have taken anatomy already. And one of the things that you do in anatomy and physiology is that you have a chapter on chemistry and cell biology where we talk about how the molecules that life is based on, where they come from and why they're important and what they're made out of. Okay. So this is the first time you guys are seeing this. Okay. For the people that have had anatomy, this would be at least the second time that they've run through this. So that's why. Any other questions?
So this does have chemistry in it. This class is in nutrition / chemistry.
Yeah, this is the limit of the chemistry part, is this chapter. The carbs, the fats, and the proteins.
Give me 1 second, because I'm gonna look at it.
It's basically how you control the diet for people that have certain diseases. Okay. How much of a carb load should they have? How much protein should they take? How much fat should they take? And then we're also going to talk about different diseases and how their diet will change with those different diseases. Okay.
Okay, so that makes sense.
Any other questions?
So I'm gonna probably be the one that's gonna ask a whole lot of questions.
That's fine.
As I'm looking at my pre-licensures for practical nursing, I took the anatomy class, and then this is nutrition. So this is part of my core curriculum. Is there a chemistry? There's not a chemistry alone, like a standing chemistry class alone. So is this the only class that I'm going to take?
Yeah. So there's not a by itself chemistry class. Okay. So if you want chemistry, okay, if you want some extra chemistry tutoring, that's probably what you're going to come to me for 5 to 7 on Friday. Okay. So we can Zoom that and I can talk to you about chemistry at your own pace so that it makes more sense to you. Okay. One of the things that, we only have like 2 hours to get through it is that we kind of have to zip through a lot of things. Whereas in office hours, I have the time to kind of make it more understandable to you. Okay. The most important thing to take away from the chemistry discussion is what the different nutrient molecules look like, what they're for, where they come from, okay, and what their roles are in the body, okay? But in order for you to understand what a molecule is, right, we have to introduce the atom and chemical bonding, and you have to understand breaking down things and building things up, right? So we have to bring those concepts in order for you to understand what happens to your food after you eat it, right? Because once you eat the food, that's not the end of the story, right? The food has to be broken down, and then that has to be put into the blood, and then we have to get that to the cells and tissues, and then they have to take the energy out of those chemical bonds and make their own kind of energy that they can use right away, and that's ATP, okay? So that's why we have to bring these concepts in so that you can understand really why you eat, right? You eat for energy and for building blocks. And that's what this course is going to flesh out for you. So if you want extra chemistry, that's no problem, right? I'm totally okay. And one of the things you might want to do, right, as you re-listen to the lecture, okay, write down stuff that's confusing to you. Okay, write down questions like, I don't get this or I don't get that. And then at office hours, what we'll do is we'll go through them. We'll discuss more in detail where you're confused, all right? And then I'll ask you questions to see if you understand. Does that make sense?
When I finish this class, because I have not printed out these PowerPoints.
You don't have to print them out if you don't want to. You can keep them on your computer, and you can type in the little areas like I'm showing you here on your computer and take the notes there. So you don't have to print them out if you don't want to.
But from my previous anatomy class, I didn't print out the PowerPoints either. But I think that I should have printed those because she closed out of the, like, I can't get back into my when I had anatomy.
Oh,
so I can't reference that.
He didn't give you handouts or anything?
Well, it was online. It was just like this.
Oh.
So now,
was there a textbook with it?
No.
No textbook?
Hold on. Anatomy.
No, it wasn't.
I did lectures.
For anatomy.
Excuse me?
It wasn't a textbook for anatomy.
But
I'm eager to tell. I'm gonna interrupt. I'm listening because I'm driving, but I want to talk to him after you. That's why I'm sorry.
Oh, that's fine.
Oh, okay, no problem.
Yeah. There should have been a textbook with it.
We didn't have to purchase it. I don't think we didn't have to purchase it because she presented. If you had, is it Elke? Is that who you had, Elke?
I had Ellie.
Yeah,
Ellie Michael.
Yeah, we didn't have to get a textbook.
Yeah.
Okay, so my question is, how do I get those PowerPoints? Because I feel that that'll be useful for me preparing for the NCLEX.
Yeah. Okay, you're talking about your anatomy PowerPoints?
I'm talking about, even going forward on how do I prepare myself to be successful in this program?
Sure. Well, these, like I said, everything that that I'm sending you is also posted on the website, and you can download it. And that includes the textbook that comes with the class. Okay. So that's all available for you to download and keep, right? The other thing that you want to do is access, and you can save the lectures, right? The links aren't going to go anywhere when the class is over. You can review the lectures as many times as you want because they'll be available as YouTube links, and those will never come down. So if you have a question about a previous lecture, then you can go back to it, and then with the notes that are provided, you can fill those in, right? In fact, that's one of the things that a lot of students do when they have a course that has a lot of stuff in it, is that in the old days, we would tape the lecture. Here, we tape it for you. And then you go back to your notes and listen to the lecture again and fill those notes in. And as you do that, you're hearing the material for a second time so that it makes more sense, okay? And you're getting complete notes. And then by writing those notes, right, or by typing those notes, it helps keep it in your head better, okay?
And that's exactly what I was doing, but I thought that I was going to have that information once the class ended.
Oh, you
and
mean
now I've learned that I don't have the lectures, because I was, after we had the lectures or whatever the case may be, I would listen, read, write, recite. That's my way of learning.
Right.
And since the class has closed, I don't have access, A, to the lectures, and B, to the PowerPoint. So
okay.
A lot of the stuff that you're talking about right now, it kind of intertwines with each other.
That's right.
Or kind of goes together.
Right.
But I can't go back to that information because I don't have it.
Okay, so there's a couple of ways we can go here. Okay, I also teach anatomy and physiology. All right, I'm not teaching it at ATA right now, but I'm teaching it at a few other schools. And if you want, what I can do is I can give you the links to the lectures for those classes, and you can listen to them, okay, for A&P 1 and 2. And I can also provide you with the notes that go to that, all right? And it's probably not the same textbook, but it's the same material. And you can go through and refresh your memory on the anatomy and physiology end of it, because it's going to be more than just what we're covering here in nutrition. And then I think that'll help you get ready for the NCLEX more effectively. Okay. So I could provide those lecture links for you and for the whole class if you like. And they're just YouTube links and they're up all the time. Okay. And then I can give you the notes to go with them, right? So that you can listen and take the notes. The textbook is, it's one that was used when we were still Beckfield. It's I can't remember the name off the top of my head at the moment. Not Saladin. It's not Ammerman. It's one of the other ones, but it's the one with had the guy in the front in the tracksuit running. Okay. And
I don't have a book, so I can't.
yeah, I'd have to, what I can do though is I can provide those notes and I can provide those lectures, and that will allow you some access to the material. Okay. The book I use is actually an old version of the book. It's an old edition, so you could probably find a very cheap copy. I can show you what the cover looks like. Let me pull that up here. The cover looks like this, and it's the book. It's the book we used back when we were Beckfield. This is like chapter 1 of the book here. And that's the cover right there. Okay. So it's Marab and Hone. Then it's Human Anatomy and Physiology. And this is an old edition. This is back 2013. So you can find this probably for almost nothing on eBay or Amazon or whatever. And then you can use that as reference material. And they even have it in the library on campus, because this is the book we used to use. But this is the book I currently teach out of, right? And the course I teach out of at Sinclair is this one, 1141, okay? So I can give you the links to all that, and then you'll have the background information that went with your A&P that you can no longer get to, as well as what we're doing here in nutrition. So if that sounds like a good idea, let me know, and I'll pump the whole course over to you. Do you think that
you can do that, please? Because
yeah, I'll do that.
Yeah, because I'm one of those people where I have to I'm visual, but I'm also, I guess I'm auditory too, so I
Right.
have to
Hear it and write it. Hear it and write it, and it can touch it. Yeah, that's why I tell people when they study, and especially in a course like anatomy and physiology, draw it, say it, write it, and touch it. You know, use as many of your senses as you can. And the approach is like the old phrase, right? How do you eat an elephant? A little bit at a time, right? One bite at a time. You do a little bit every day, and that way it sticks, right? So you don't have to cram everything, do little pieces at a time. It makes it stick more easily. So I can give you these links. I'll give you these links, and I'll give them to anybody else that wants them, that had and then lost the A&P, and you can use them, and then we can try and find you a good price on that text. And like I said, I think it's in the library at ATA, because this is the text we use. So I'm happy to do that for you. More than happy.
Matt, can you please do that for me? I mean,
Yeah.
because I am just.
Yeah, I'll do that. And that includes a very good discussion on chemistry, okay? Which is what we just kind of finished. In fact, a lot of what I took from this lecture came from that textbook, okay? So you'll see some of those slides again. So I'm happy to do that for you, okay? So I'll provide that. I'll make that like a resource for the class if they're interested. And then they can use that as a refresher, okay? Are we cool? Got anything else?
Yes, I'll probably be, if I may be contacting you or reaching out to you for the, for additional help on Friday from 5 to 7.
Yeah, absolutely. I got no problem with that. Yeah, what I'll do is I'll I'll set up a Zoom for Friday, and you guys can just pop in, and this will be for not just you guys, but for all the other classes I teach, and I'll answer you guys' questions. I got no problem with that. Okay.
It was challenging today for me to get in using that password.
Oh yeah, that was something that changed. That was an ATA policy because we used to not require a password, and you would just be in the waiting room, and I'd let you in. But they want you to just be able to go in on your own with the password. Just remember, it's all capitals, NUT 100.
Is it always going to be that?
Yeah, it's always that.
Okay, so going forward, that's going to always be the password,
That's
and
right.
then
Mm-hmm.
would I have, when I go back to re-listen to this, would I still need to use that password?
What you'll get is a link in your email. It'll be a YouTube link, and you just click on that link, and you'll go right into the lecture.
I think those are all my questions. If I have anything else, I can email you. The number is not valid until Friday between 5 and 7, right?
Right.
Okay.
Cool.
Yes, thank you.
Welcome. Glad to do
Bye-bye.
it.
Thank you,
Bye-bye.
Dr.